Hello everyone, welcome to our online workshop. My name is Zidan. I am a PhD student. Um, my work is mainly focusing on AVO inversion using prior information derived from rock physics modeling. And in this presentation, I'm going to show you how we can use machine learning in performing the AVO both preconditioning and inversion. So this is a little background about AVO modeling. So AVO modeling using the convolutional modeling example. So the seismic trace can be represented by a wavelet that is convolved with seismic reflectivity and some added noise to it. So using the time continuous reflectivity theory and assuming weak contrast between model parameters, we can express our seismic traces in terms of uh, a linear operator G, which depends on the incidence angle, and the model parameters M, which in that case the logarithm of the logarithmic of the model parameter like VP and VS and rho, and also some added noise to the data. So this is the linear inversion form of the AVO inversion. Um, most industrial or even academic work for AVO inversion are using Bayesian theory to perform the inversion. And a little background about Bayesian inversion. So in Bayesian inversion, model and data and also the noise are assumed to follow normal distribution. And by this assumption, we can divide our model into background model and some perturbation of that background model. And by doing that, we can construct a covariance matrix that relates every model parameters to each other. The Bayesian inversion in the general form is very efficient if the model parameters are only one model. In other words, 1D inversion. So in 1D inversion, you can efficiently estimate the filter that is based on the covariance of the 1D model, or the covariance of that model, which is the variance of that model. The Bayesian theory becomes okay or can be applied with the certain of uncertainty when the model parameters become more than one and become two. So in case of 2D inversion, for example, you have VP and VS, the Bayesian inversion still will give you a good results because you can construct a fair model covariance matrix. But when the model parameters become more than 2, 3 or 5 or 7, the Bayesian inversion becomes inefficient because the covariance or the model covariance now becomes inaccurate because you have multiple dimensions to construct the your model covariance. And also we have the data covariance, which tries to characterize the noise in the data set, which is impossible to know because we don't know exactly what kind of noise included in our data set. So the Bayesian used both information about the model covariance and the data covariance to estimate the posterior distribution and try to enhance this posterior distribution by obtaining the best model parameters given the data set. So for you to use a Bayesian inversion, you need to have an accurate model covariance, which in case of more than 2 parameters is very difficult to get that accurate representation of the model parameters. And also you need to have the data covariance. Again, you don't know the all the noise characteristics that are included in your data, and also you need to know an efficient or robust model background. So in our proposal, we propose to use machine learning in both preconditioning and inversion of the dataset, and by using the machine learning approach, we don't have to estimate the accurate representation of the data covariance matrix, and also we don't have to estimate the exact representation of the model covariance matrix we have. So we can use machine learning to precondition and to invert the data without knowing those two parameters. So now, where to get the labels? So the most important questions in any machine learning approach is, where can I get the label? So we will answer this question in the next slides. So this is the piece of data, which is a well log we have. For example, the VP and VS and rho in this data set. And this is the model parameter variation of the model parameter variation relationship between each other, and we can see that the VP and VS relationship is more than the relationship between the density and other parameters. So first, we will introduce you the conventional preconditioning approach that is used in industry before doing the AVO inversion. Those conventional methods include bandpass filter, trimestatic, averaging gathers, and parabolic gradient transform. So mostly the bandpass filter and averaging gathers are used to try to reduce the random noise in the dataset. Parabolic gradient transform also used to reduce the random noise in the dataset, as well as the multiples in the dataset. And the last one is the trimestatic. The trimestatic used to correct for the time shifting included in the data due to low velocity layers or tomographic or any kind of static error included in the dataset. So in the next slide, we will show you some processing flow involving a combination of all of those processes to correct the real data. So here we performed 3 processing flows. Each flow is a combination of different testing parameters for different flows from the previously stated processing steps, and we can see that maybe processing 4 and 5 and 6 are the most promising steps. If you compare between the raw data and those processing, we can see it efficiently correct for the static shifting and some random noise in the dataset. And for further investigation, we can take an event and start to analyze it. So we can see that the cyan color is the raw data, and the other colors are the different processing flows. And we can see that it corrected the real data. For example, the processing 5 corrected the static shifting and the far offset efficiently from the real data, and also corrects some random noise in here, but it is still preserving the response of the AVO response of that event. So we have 2 major problems in preconditioning of the dataset. The first one is so this is an example of the measured data, and this is an example of the model data. So at the same time event, this is the measured and this is the model data, and you can assume that this data comes from that by adding some random noise about the model data. but this assumption is too weak because, as we explained before, you can efficiently get rid of the random noise. Not efficiently, but by 90% you can get rid of the random noise. So assuming this type of error is purely random noise is a wrong assumption. And the second thing is, you may have this event which has a certain response by starting large negative and become less negative with offset, but its model data is the opposite. It starts at less negative and become more negative with offset. So it's not only the noise in the dataset, but it is also the AVO response of the dataset. So those are the two major problems in comparing the real data and the model data. So in comparison between both, we have two problems. The first one is the noise in the dataset, and we cannot simulate this noise by a simple random noise only. The second thing is the difference in response, in AVO response, between the model data and the real data. There will be unpredicted patterns in the model data that we cannot predict in our network. This is a real example on our data, which shows the difference between the AVO response between the real data. In this case, this is the real data AVO response, which suggesting that this is a type 3 AVO response, and between the model data, which suggested that at that event the AVO response should be of type 4. So this is a real example on how the model data AVO response differs from the model data AVO response. So this error needs to be corrected before using the linear operator. So how we correct it? By doing a further analysis to our real data, we saw that between adjacent CDPs the noise level is low or is very low between two adjacent CDP. For example, if I take this CDP and I look to the next CDP who's taking a certain event, we can see that the noise level or the noise characteristics between two adjacent CDPs are not that different. So by knowing a certain piece of information at one location, I can predict what this piece of information should look like in the adjacent CDP. So the only piece of information I know is the real data at the will log location and the model data at the will log location. So those are the two model, or those are the two the piece of information I know, which is the real data and the model data at the well location. So the first network we are trying to build is a network that takes untrustworthy data set and give us a prediction of a logic data that we can understand and we can deal with. So we previously mentioned that this approach is better done if we have more than one well log. For example, if we have 2 or 3 well logs at different locations. So now we have only one will log, so we need to train our neural network in a stepwise fashion because of the lack of more information than we have. So we decided to divide our survey into batches, and we will take each batch separately and train and try to predict each batch separately, and then the next one and the next one and the next one, and all are done in parallel so that we can reduce the uncertainty predictions in our uncertainty in our predictions. So to further explain our training strategy, so this is the will log location and this is the batch one at the will log location, and moving backward to the very first CDP in the location, this is the kind of batch we are trying to predict, and moving forward to the very last CDP in the survey, this is the batch we are trying to predict. So to do that, we need to use the ensemble learning approach, and in ensemble learning approach, we need to reduce the uncertainty between predictions. As I said before, our training will be in a stepwise fashion, so you don't add all your data set at once. So you add it in a stepwise fashion in the network. So by doing that, we not only using the current model, we also using the previous model. So by doing that, you are reducing the uncertainty between predictions. So every time you predict and then you go further, so this kind of ensemble learning will reduce the prediction error or the uncertainty in the predictions. So this is the a small piece of results showing the will log location and the two prediction location we are trying to perform, and this is the result. This is the primary result of our network, and we can see that the original or the real data has all kind of noise involved in it, and we are trying to estimate and remove those noise based on our information on the modeling process. So by doing that, we can estimate what this event should look like in our model data, so we can predict that position and that position based on the previous position because of the characteristic we showed before. The adjacent CDPs are not the big difference between adjacent CDPs. So this is the results if we talk one event, and so this is the event in the real data, and this is the event that should look like in the prediction. So when I invert the data, I cannot handle or I cannot deal with this, but I can deal with something like that. So now, instead of having untrustworthy data, I have some logic data that I can understand and my linear operator can understand as well. So the second model or the second neural network we are trying to build is a neural network that can do the inversion itself. So how we do that, we previously mentioned before, when using the network, it's better because now we are not restricted to only one covariance matrix based on one piece of information we have. But if we use network, we can have more than one model covariance by creating more than one realizations from the piece of information we know, which is the will log location. So every time we create a realization from that information, we are including different model covariance of the data. So every time we do realization, every time we create different model covariance of the data, that is going to feed into the network and try to predict the model parameters from that kind of modeling or linear operator. So the process is very simple. So we have the will log information. We can create mini realization from the will log information based on Gaussian or Gaussian mixture or any clustering approach or method we prefer, and then we do the forward modeling to create the angle gather. We then train the angle gathers to predict the model parameters. So this is the angle gather will predict the model parameters, and then we can use the trained network to predict our model parameter using our piece of data that we already corrected in the previous stage. So this one shows how the inversion is working. So we are used a full bandwidth of the data, which is 30 Hertz, and we are trying to predict the model parameter variations. We can see that at a certain location the prediction is good, but at other location the prediction is not that good. So when we reconstruct the estimated model parameter variation, we can see that. So the red one is the label, and the black one is the predicted. We can see that the prediction is very good, resembles the real data here and here, especially here, and that difference related to the inefficient training of the network. So the network needs to be trained more and with more examples. And also we try to predict some low frequency model of the data by using only 50 Hertz of the data, and so this is the model parameter variations using the 50 Hertz. And when we reconstruct the model, we can see that the inversion using neural network is very good approximation of the real data. So it could predict this kind of boundary, and it could predict that boundary, and also could predict that boundary here, and this is the major boundary it could predict in here and also here. So it is efficiently reconstructing not only VP and VS but the density as well, and this is the major advantage of using the neural network that is efficient enough for inverting the three parameters VP and VS in a row, and maybe further if we include the Thompson parameters. So in conclusion, we could efficiently use machine learning to do preconditioning of the data by correcting the real data of its noise or of wrong AVO response using the machine learning rather than conventional processes. And also we can use the machine learning or neural network to perform the inversion itself, because the neural network can handle more than one parameter, 2 or 3 and maybe 5 or 7. So that was the end of my presentation. Thank you very much for your attention, and I hope it was good presented. Thank you very much.